Hello, everyone. Welcome back to the AAS YouTube channel. And this is part of the good stuff. This is part of the great stuff. This is the AAS Journal Author Series. And I am delighted to have Manisha Shrestha with us today. Hello, Manisha.
Hi, Frank. Thank you for having me.
Well, thank you for agreeing to talk about your very awesome article, which we'll get to here real shortly on this April 11th of 2025 as we record this. And Manisha, what's your geolocation? Where are you at?
I'm currently at Tucson, Arizona, very close from you, actually. And it's
We're
getting,
neighbor at about 90 miles, 100 miles or so, depending where you go.
yeah,
We're close.
yeah, I'm hoping it's not as hot as here. I don't know. Is it hotter?
In general, no. In the summer, the valley, the Phoenix Valley, will be a few degrees hotter than Tucson, in part because it's lower, so sit deeper in the valley, and so yeah, we get the reflected sun. Um,
Mhm.
so yeah. So how is spring in Tucson?
Oh, this is definitely my favorite part of the
Ah,
year
good.
because
Good.
I don't know, I didn't grow up around a lot of cactuses, so like having them bloom
Yeah,
is so
yeah, it's very
pretty.
cool.
Like, and some of the plants look very alien looking.
Hmm.
Palo verde with the green trunk and yellow flower are my favorite. So,
Very cool.
this is my favorite season.
Very cool. Yes, yes, yes. One of the more enjoyable ones, at least until you wait until maybe November or something when it cools off, because yeah, we're coming up on the blast furnace here. So, and Manisha, what's your position there at Tucson Stewart?
Yeah, I'm a postdoctoral researcher here at Stewart Observatory.
Hmm.
I work in David Sands group.
Okay, very cool. So as long as we're there, let's go ahead and go there. And Manisha, what do you like to do for research?
Yeah, so I'm very excited about everything that explodes. So
Ah,
I work on
okay.
different kind of transients. I am very interested in looking into gamma ray bursts, one of the most energetic explosions. I'm also very interested in different kind of supernova, mostly core collapse though. Like I
Yeah.
like massive stars, not very low mass star person. And another thing, like we are in collaboration with Northwestern University, and our
Ah,
collaboration is called Saguaro, since we are from Tucson.
there you
This
go.
is for looking at electromagnetic counterparts of gravitational waves. So different kind of transients, like everything that is exploding, I'm very excited to study. And I do mostly observational studies of these objects.
Very cool. Well, you're at the right place to get some telescope
Yeah.
time. Very cool. And that is going to bring us to this very awesome APJ letter. It is open access. It's the open access era, people. You can go grab a copy for free. Go get one. Spectropolarimetry of SN 2023 IXF reveals both circumstellar material and an aspherical helium core. And Manisha, take us away.
Great. Thank you. So as you can see, the author list is pretty long. Um, my second author here, I want to give a shout out to her, Sabrina, who's a graduate student at University of Denver. So this work is very interesting and also near to my heart because this brings collaboration of my PhD group, my previous postdoc, and this postdoc. So
All
like
right, we got three going there. Very good.
yes. So I got to work with my PhD supervisor, my previous postdoc supervisor, and current supervisor. So this is a very exciting work.
Cool.
So here, what we are studying or looking, this paper is doing is using polarimetric data, both photo imaging polarimetry and spectropolarimetry data,
Okay.
to study this very, very nearby. It is around 6.85 megaparsec away in M101.
Okay.
This very exciting core collapse supernova. So with the kind of distance it is in, it is like once in a decade kind of core collapse supernova. So very, very nearby. And this was studied a lot. There are right now 55 peer-reviewed papers there on this
Very good. Very good. I'm impressed.
so
I'm
it's a
impressed.
very, very well studied supernova and it's so close by. So our paper does one aspect of studies.
Okay.
So most of the time in astronomy, right, we are getting the data of emission or light, and we study the properties of light to get information about that astrophysical event. And so a lot of time we study photometry, that is the imaging, we study spectroscopy, but a lot of time we miss polarimetry, which
Yep.
also gives such important information and bring together the whole picture.
Mhm.
Because this was such a close by event, it was bright enough that with polarization, we were able to get very good set of data.
Cool.
So this paper ties in all the things we have been seeing from other emission, like from spectroscopy, from photometry, and brings everything together and gives a very good complementary results to show how much we understand about this supernova. Because I think this is one of those where, like if you work in supernova, like the 1987A kind of supernova, that we will use it a lot in future
Wow.
to
Yeah.
understand these farther away supernova that we might not have good data set, but
Right.
with whatever data set we have, we can compare it with this gold sample data and get much more information.
Cool.
So I will talk about what we did and what are the different results we get and how it ties into all the other papers that have been out before. Before I
All
do that,
55 of them. All 55 of them.
so before I go to that, I will
Okay.
ask Frank to move to the presentation.
Sure.
While
We have a
he's
little
doing that,
bonus material here for you people.
yeah,
We have a little bonus material. Go ahead.
yeah. So this is beautiful, beautiful picture.
Mhm.
This is M101, so a lot
Yes.
of people have a lot of beautiful picture of this, but you can see the 23 IXS right there. It's
Mhm.
very bright. It's very close by. That's why we observed it. We got a lot of data. The reason I'm switching from paper here is I just wanted to give you a quick refresher on polarimetry so
Please.
that you can follow along once I start to talk about the paper. We can go
Okay.
to the next slide.
Next one. Here we go.
So there's different ways to polarize light. Here, I will be talking mostly polarization coming from electron scattering.
Okay.
So what I mean here is you can have one photon coming through that gets scattered by electron, and that can introduce polarization.
Yes.
Now, how this works, if you have something like a spherical structure, like in this figure, so it is spherically symmetric. So one photon, when they get scattered, can be polarized. Like you can see one straight line there, right?
Yes.
But because these are so far away, we just see the resultant light.
Yes.
So one photon can be polarized, but everything cancels out. So we don't see any polarization if it is spherically symmetric.
Yes.
Now, if we could go to the next slide, if we break this symmetry somehow, for example, here, one example is we elongated this scattering region, then you can imagine, you can see that some of them cancel out, but resultant, there is exactly some polarization left.
Yes.
This kind of like overall asphericity introduced something called continuum polarization.
Okay.
Now, if we go to the other slide, there are other scenarios where you can have these clumps. That is just like some stuff that is
Mhm.
blocking this light
Yes.
emission coming.
Yes. Mhm.
In that case, this actually arises and gives you something called line polarization. So we are basically, in a very simple way, breaking the symmetry of scattering region and introducing polarization.
Okay.
So there are many different ways you can create polarization, but for supernova science and what I'm going to talk about is something like this. And before we start the next slide, I just wanted to I will be talking about Stokes vectors very, very quickly. I
Yes.
will try not to use too much of it. But you have three Stokes vectors here, like Q, U, and V.
Yes.
Q and U are linear polarization, as you can see here.
Yes.
And V is circular polarization.
Huh.
In supernova, when you have this very energetic explosion, most of the things are very highly heated. So you expect a lot of electrons to be there, right? And
Yes.
this electron scattering cannot produce circular polarization. So when I'm talking about polarization moving forward in the paper, I'm just talking about Stokes Q and U. There is no Stokes P. Okay,
Okay.
now we can go back. I hope that will help you to go through once we go through the paper.
That was very useful. So yeah, that's good. Okay, let's go back to sharing the article and boom, here we go.
Perfect. So one of the great thing, like with core collapse supernova, so these are explosion of very massive stars. At least it has to be 8 times the mass of sun.
Okay.
So these explosions are very important in a lot of different ways. A lot of heavy elements, that is heavier than helium, are produced in center of these massive stars, right? And
Uh-huh.
when they explode, they expel all of this stuff in the local environment. So
Okay.
it has impact in many different levels, from understanding this massive star evolution to how it impacts the local environment of the galaxy, and also how these heavy elements are formed. So these are very interesting. However, we have a big gap in our understanding of how this very massive star loses mass throughout its lifetime.
Yes.
So we know, so here I'm talking about normal core collapse supernova, that is type 2.
Okay.
So around 70% of core collapse supernova, that is explosion of very massive stars, are these type of supernova.
Yes.
So in this case, we want to understand, and one of the big puzzle we have is how much mass loss happens, and especially right before the explosion. It is very limited. We don't know. A lot of observational studies have been done and used with a theoretical model to get mass loss rate, but
Yes.
different models predict like orders of magnitude different mass loss rate.
Yes,
So
it is.
depending on which model you use, you might be saying, oh, this is the mass loss rate, but it will be so different from the other model.
Yeah.
Another difficulty with this is that, as you can imagine, just massive stars in other galaxies are very hard to observe, right? They are pretty faint in other galaxies. In our galaxies, we can see them. We see clear sign of mass loss in the form of this beautiful stellar wind bow shock, if you have seen around Betelgeuse or Zeta Ophiuchi.
Good.
So we know these massive stars are losing mass throughout its lifetime, but we don't know how much. And that is very critical information because this mass loss impacts how these massive star ends its life,
Yes.
right? Like how much mass has gone through will dictate how these massive stars explode. So
Okay.
that is one thing we are very interested in understanding. And
Cool.
one of the way to do that is to use very early observation of supernova.
Uh-huh.
Now, supernova are much more brighter than massive stars,
A little
so we
bit.
can study them in other galaxies as well. So in our group, we are very interested in using this very, very early data and try to get information about mass loss rate.
Cool.
And the way we do that is this ejecta from this explosion interacts with circumstellar material
Mhm.
that's created by the mass loss.
Uh-huh.
And this interaction leaves imprint in all aspect of emission coming from that, from photometry to spectroscopy to polarimetry.
Yes.
And so for 23 IXF, there is a lot of good data. So I want to give another shout out here that it was discovered by Itagaki, who is an amateur astronomer in Japan, and he discovers a lot of very, very interesting supernova that we follow up.
Yes, he
So,
did.
and here, because it was in M101, there were
Hmm.
a lot of data from amateur astronomers
Hmm.
even before the explosion happened. So we have this amazing great set of data that
Cool.
has been published in other papers too. Like our group have multiple papers out on this.
Uh-huh.
So my research is more looking into the polarimetry of this.
Cool.
Now, why do we want to do polarimetry? You might be asking. So, like I said, we are very interested in understanding the circumstellar material
Mhm.
of these mass loss to constrain mass loss. And from spectra, for example, there is something called narrow emission lines, which are basically, if you look at spectra, you see this very narrow line. The reason it is narrow is because you have something almost stationary, circumstellar material. This
Okay.
ejecta that is moving very, very high velocity interacts, and then this creates emission line. But since this one is not moving, it creates narrow emission lines. If
Okay.
it was moving, it would be broad
Wow.
because you have this movement of the emission. So these narrow emission lines tells you that there is CSM present.
Okay.
And we know for 23 IXF, there was narrow emission line for almost 5, 6 days. So this lasts
Okay.
quite a long time. So we know CSM interaction or circumstellar material interaction is happening. So we wanted to get more information about this circumstellar material
Yeah.
using polarimetry.
Okay.
In the few slides I showed you, polarization emission depends greatly on how does the circumstellar material or the scattering region looks like, right?
Yes.
So that is why we were very interested.
Mhm.
And there are a lot of studies before, mostly for this other kind of supernova called type 2N. So in this one, we know there is very, very dense circumstellar material, and
Yes.
that narrow emission line lasts for many, many days, not like few days, like in type 2P that I'm talking about.
Okay.
So here you can see we have a lot of like observational study of these type 2 supernova. And then there are models. Nagao et al. Had this large lot of observational for different type 2P supernova studies to understand how does this polarimetry looks like for different kind of type 2 supernova. And so our work for 23 IXF, here you can see in the second last paragraph for this paper, what we did is we got spectropolarimetric and imaging polarimetric data. And so we are going to present about that. So now, so with this in mind, and there are other two paper on polarization of 23 IXF as well. So I will try to bring together what we can learn just from polarization side of the thing.
Very cool. Very cool. Okay,
Okay.
I'm with you. Mhm.
Perfect. So for observation, we use two different instruments. First, here you can see is something called MOPTOP. So it's an imaging polarimetry instrument that is working in optical bands. And so this is if we go slightly below,
Mhm.
this is on 2 meter class Liverpool telescope. It
Yeah.
is Liverpool telescope, but as you can imagine, the weather in Liverpool is not good. So it is in La Palma. But this is an
Mhm.
instrument that I
That
work
works. Works
with
great.
a lot. So this instrument is actually designed to study polarization from transients,
Nice.
but this is more designed for gamma ray bursts than supernova. But this is very good when you want to get something that is evolving in very, very short period of time.
Yeah.
So we used this polarimeter and we got data in BVR and I filter.
Cool.
So the first data set is around 2.3 days after the explosion, not discovery.
Okay.
So another paper that I was part of from Griffin, Hosenjada, this paper calculated when was the explosion epoch based on all the photometric light curve they
Okay.
have. And they
Mhm.
used some modeling to see where the explosion might have happened. So this will be a little bit different from the discovery.
Yes.
And so our first data set is from 2.3 days, and our last data is from 76
Yeah,
days. So
good.
it covers quite a large area, and you will see that in a paper, in a plot later on. So
Cool.
with this instrument, it is a little bit different from normal polarimeter. If you know, like a lot of polarimeter have a halfway plate
Yep.
that rotates to 4 different angles, and then we calculate Q and U.
Yes.
This is slightly different. We get 16 different images. There is a paper where we describe all of this, how we do it.
Okay.
I won't go in much detail here, but basically it is designed so that we can rotate the half-wave plate very, very quickly.
Yes.
In most of the normal instrument, we just rotate it, slowly. Lot of for astronomical transients, it doesn't matter. Sorry, astronomical sources, it doesn't matter because they don't change that quickly. However, for something like gamma ray bursts, it changes very quickly. So we want to be able to rotate it fast.
Quick.
So we got this data, lovely data, and then we reduced it. After the flat fielding and dark subtraction that happens in the instrument itself,
Yes.
we used data reduction pipeline that we have developed and calculated Stokes Q and U, as you can see there, and then calculated what is polarization. One interesting thing with polarization is that this Stokes Q and U, you can see it is square root and squared of Q and U. So what it means is that we are squaring, if there is noise in Q and U, it adds up and makes polarization larger.
Yeah.
So we need to be careful, especially when it is not highly polarized source, to make sure that we are not introducing this bias.
Right.
Right?
Right.
So in order to do that, we do correct for this bias in our all of the analysis following this paper there. Yes.
Mm-hmm. I won't attempt to pronunciate that.
Yeah, I'm not gonna do it either.
Okay.
And then after MobTop, we also get data from Arizona from instrument called SPOL. So this
Oh,
one does
yeah.
spectropolarimetry, and
Mhm.
it is also in optical wavelengths. And for this, we use 2.3-meter telescope Bok
Yep.
in Kitt Peak here.
Yep.
And for this one, we got our first data at 12.4 days after the explosion. And then we have this set of data going up to 31.57 days. So again, in this is more traditional polarimeter. So
Mhm.
yes, you can see in the table like all the different instrument and when these different data were taken.
Here's the P's. Okay.
Yeah,
P
those are percentage. If you're not used to with polarization, 1% is pretty high.
Yes. Yes.
So yeah. So we calculated again spectropolarimetry. This reduction was done using IRAF pipeline we have, and we calculated Stokes Q and U, and then calculated polarization and position angle from SPOL as well. So these are the data we have.
Mhm.
Now we want to do analysis of this. And the error for SPOL data is much lower than error for MobTop data.
Okay.
So now, if we go down,
Sure. We got down. Let me go to
okay,
3.
perfect. So now I will talk about results. But before I talk about result, one of the very, very kind of headache that a lot of observational astronomer who have to do polarimetry will tell you about is interstellar polarization.
Oh, yes. That kind of, uh-huh.
Uh-huh. So we are getting this emission, right, light from this faraway object, but there are stuff between us and that transient.
Does.
And a lot of time we are talking about interstellar dust.
Yeah.
So this dust can scatter light and introduce polarization as well. So in order to get the intrinsic polarization that is coming from the source itself, so we want to detangle it,
Yes.
like from what we are getting versus what is the intrinsic polarization of the source itself, we need to figure out what is the stuff between us and the transient is doing.
Yes.
Now, there are two main things. One is dust in our own Milky Way galaxy,
Yep.
and the other is dust or stuff in the galaxy where this supernova is, that
Oh.
is M101.
Okay. Mm-hmm.
And in this paper, there are multiple different ways to approximate this because it is a very hard thing to do. In our paper, we use two different techniques so that we can check if we are making similar kind of interstellar polarization
Good.
before we reduce them. So the first one is, it's a very old technique that have been used for quite some time, and it is done using empirical data. So
Okay.
from Tarkovsky, 1975,
Wow.
what we have is that we have this very empirical data. If you go, the PV is less than 9 times EV minus V.
Yeah. Hmm.
Yeah, right there. So this is coming from observation of uh, lot of um, sorry, a lot of stars and other thing in our galaxy. So this is for our galaxy. We can calculate polarization and then map it and create like an empirical structure. How does polarization changes? And this seems to be related to this EV minus V is basically dust extinction value.
Okay.
So what we did for the first technique
Okay.
is to look at what is this EV minus V, or the dust extinction for our host galaxy is.
Yes.
And for this, we have this very good data set. If you go slightly up, from Safley, from 2011, there is like a lot of like this data from IPAC, a repo you can find. Looking at different coordinate, we can
Uh-huh.
calculate what is the extinction for Milky Way in that direction is. So
Right.
that for the Milky Way. For the host, it can be a little bit difficult, challenging, because we don't have this kind of data set. But here, thankfully, because it is so close by and there are so many data, we had this lovely high resolution data, again, from Arizona as well, but from different instrument. And using that, Nathan Smith and from his paper, they calculate host galaxy extinction to be this value. So we have extinction, dust extinction, both from the host and Milky Way.
Okay.
And we combine them and calculate this, what is the maximum ISP it is from if both of these dust in the Milky Way and the host were aligned. So
Okay.
it has to be
Yeah.
aligned, because if
Yeah.
it is not, it will cancel out. So when it is aligned, so this is the maximum possible, at
Okay.
least from dust extinction itself.
Okay.
So we calculated this. So from this, we get that the value is around 0.35%. So if all of this dust were aligned and introducing polarization, the upper limit is around 0.35%.
Okay.
And there are other papers as well. And all of our ISP estimate matches pretty well from this method.
Very good. Okay. Cool. Beautiful.
So this
Okay.
maximum ISP is for V band. So there is a relation to convert it into different wavelengths so that we can calculate for R, I, other filters as well. So we
Good.
use this relation and then calculated what it is in different filters.
Mm-hmm.
Right.
Okay. Yep.
So this is what we did from one of our method.
Okay.
Now we wanted to make sure that from another method we get similar value, but also one thing you will see here is that we are calculating maximum polarization value, not Q and U.
Yes.
Now to subtract Q and U, or to get rid of this ISP, it is very difficult. It is like vector addition or subtraction you can think of. So
Okay.
we cannot do that with just P. We want this Q and U.
Yes.
So here for the second method, what we do is we look at this H alpha strong emission line. So the idea is that this emission line is coming from
Okay.
resonant scattering rather than electron scattering.
Yeah.
So this is supposed to be unpolarized. So this scattering will unpolarize the light, and then we see a dip in polarization rather than emission.
Yeah.
And so it will be less than continuum. And this dip should give you what is actual interstellar polarization is.
I'm with you. Cool.
Okay, great. So this is the technique we used. And in one of the spectropolarimetric data from June 14, we see this very clear H alpha emission. And so we used that area. And then we calculated what is Stokes Q and U at that line is. And
Yeah.
now you can imagine it's a bit complicated because like that line can be of different width and we need to figure out exactly where. So what we did is we changed different beams to
Okay.
make sure that just changing beam, we are not changing what is the interstellar polarization because it shouldn't be, right? So we did that. We checked from 100 to 200 angstrom of binning, and from that we calculate our Q interstellar
Okay.
and interstellar as shown there. So
Okay.
that is what we did. We calculated this.
There we go. Uh-huh.
Perfect. And from here, we find our polarization from interstellar to be 1.3. So that is less than what we expected from
Uh-huh.
the maximum from the extinction itself.
Well, that
So
part is good.
we are pretty, it seems to be doing the thing we wanted to. So we calculated this and we reduce this or we subtract this from all of our observational data to
Yes.
detangle and get intrinsic polarization.
Very good. Cool. I'm with you.
So now let's go to the intrinsic polarization.
Mhm.
So first, we will separate it and we will talk about continuum polarization and imaging polarimetry.
Okay.
So for the continuum polarization or imaging polarimetry, here we are looking at one filter data. So from MobTop, we got this data from BVR and I filters.
Yep.
And so we calculated how does this polarization is evolving with time.
Yes.
And in order to supplement our data from MobTop, we use one wavelength range in our spectropolarimetry data and binned it error-weighted average of continuum to calculate what is an equivalent R-band data.
Okay.
If you go down in this figure, I know we have figure one, but I wanted to talk about this figure first.
All good. All good.
Perfect. So in this figure, I know there are a lot of things. Let's take one step at
Yeah.
a time. On the top, the red data points are R-band magnitude.
Okay.
This is from a grad student's paper, Brian, who is here at UFA. And it is coming from LCO data. So you see this beautiful light curve. So
Yeah.
in R band, you see this initial rise, and then it is almost like a plateau. So that is where the type 2P comes from. And
Yep.
then we have this falling from the plateau.
Yep.
The black data points are our polarization data.
Ooh,
So
okay.
here we have, you see different symbols. So we have like, we try to include all the published data from Singh and Vasilev, but also our data that is SPOL and MobTop data, just to put
Yes.
clear whole picture what's happening.
Cool.
So what you see here is in the very, very first few data points, that very high ones. So that is our first data points. That is when the light curve is going upward.
Okay.
That is where
Yep.
all those narrow emission line that I was telling you about in the spectra, that is
Uh-huh.
where the flash feature or what is showing their CSM interaction is happening. That's where these first data points are in polarimetry. So pretty high level of polarization. It's like over 1%. And this is intrinsic polarization.
Yeah, yeah,
That
yeah.
is very high. And that on the bottom is position angle.
Yep.
That will come into very important, like what is the scattering region looks like. So initially, we have this high level of polarization, and we have this little bit over 150 degrees of position angle.
Uh-huh.
Now the light curve is evolving, and this polarization starts to go down.
Yes.
And once we actually settle well on the plateau, so those three dashed line, vertical dashed lines are basically, the first one is where we have this very high level of polarization detection.
Mm-hmm.
The second one is tentatively where you have the peak in the light curve in the photometric data.
I'm with
And you
you.
can see after that peak in the light curve, the polarization starts to go down. And
Yes. A little bit.
it
Mm-hmm.
is kind of very, very like close to very low level of polarization.
Mhm.
And then once it falls from the plateau, the third dashed line, you see this jump in polarization. We
Yes.
see this higher level of polarization.
Okay.
Another interesting thing on the bottom panel in the position angle,
Yes.
initially you have, around like the first peak is around like 150, 56.
Yes.
But then it rotates and it goes almost by 90-degree difference in the point when it starts to go away from the CSM interaction being important. So that is very giving us very important clue. And I will bring all of that together just in a moment, but just keep that in mind.
I shall. I shall.
Okay. So if we keep going down,
Top T. Let's see. So you guys see.
so here on the top, I just wanted to point out in the previous page,
Yes.
sorry,
Sorry.
yeah, here. I just wanted to point out that it's not just one data point. Like we see this behavior in other filters as well. Like we
Yes.
just saw the R-band polarimetry, but we do have data for BV and I from MopTop, but we don't have for the during the plateau phase. That's why we didn't show it there.
Okay.
But all of this
Yeah.
variation we see in each and every filter. So this is not like some kind of, anomaly. It's more consistent in all different filters.
Okay. Cool. Good. That
Okay.
helps.
So if we go down this sketch,
Okay. Get that. All right. Good. I'm with you there. Okay. On to figure three.
so this sketch is a way to bring everything together to give you a sense of what is happening when this explosion went off.
Okay.
So here in the first figure, like the first part of this sketch, you can imagine this star, a massive star that was surrounded by this circumstellar material. Now, the circumstellar material is the gray region, and you have this very massive star at the center.
Okay.
This massive star exploded, and this ejecta is interacting with this circumstellar material.
Yes.
You are getting most of the emission or the light we are seeing is coming from this interaction that happened, right?
Yes.
And this is proven also not just by polarimetry, but also with spectroscopy. We have very good data set that shows this is happening. We know this is happening.
Mm-hmm.
So when you have this interaction, there is a lot of free electron, and this electron scattering is producing polarization.
Yes.
Since we are getting almost 1% of intrinsic
Right.
polarization, that is a lot.
Right. Large.
Yes, it shows that we have this asymmetry or asphericity in this scattering region that is giving us a resultant polarization. And
Okay.
like I said, the position angle changes too. That is interesting because if you look at those arrows there, the red arrows there,
Mm-hmm.
that is giving you in what direction the resultant polarization will look like.
Okay. Mm-hmm.
Now, this explosion happened, this photosphere is expanding with time, right?
Yes.
And
Yeah.
it is expanding. Our first spectropolarimetry data that we got is around the peak of the light curve.
Okay.
And in that time, we see this 90 degrees flip in
Yes.
polarization angle, but
Yeah.
we do detect some level of polarization. And what we think is happening is you still have that circumstellar material in one plane.
Yes.
This photosphere expanded, but there is like, it hasn't engulfed all of the CSM. So in the west area, there is a small portion where interaction is still happening.
Yes. It hasn't quite cleared.
So now the emission is coming both from this scattering in the west, but also from the photosphere, right?
Yes.
And so the resultant polarization have switched by 90-degree now,
Yes.
just like that arrow there.
Mm-hmm.
But we are getting some level of polarization here.
Mm-hmm.
Now, we think one of the big reasons why we think that is happening is also a lot of work have been done to look at photometric data itself and to see that if there was no CSM interaction. Will the light curve looks right or not? And people have found that in this very peak, a lot of time, a lot of these type 2P supernova, the light curve fits much better when there is some circumstellar interaction happening rather than
Okay.
without. So we think there is two different ways that we are seeing this interaction happening.
Yeah. Okay. Cool. Makes sense.
Now, like it is expanding, expanding, expanding photosphere.
Yeah.
Once we are in a proper plateau phase where there is basically the photosphere is the main emission reason, it is spherically symmetric. So we really don't expect
Yes.
much polarization there.
Right.
However, once it falls from the plateau, then you see this jump in polarization.
Uh-huh.
And that is where what we think is happening is that the photosphere have become so optically thin that
Yes.
we are starting to see the inner core
Yes.
where this could be aspherical, and that is increasing the polarization. Now, this phase we have seen before in other type 2P as well, this
Okay.
jump in polarization.
Okay.
So we think that is what is happening. Now, there are models from Luc Desart, which we compare it with our observational data, and they also see a jump in polarization, but the way they explain is slightly different. So what they think is happening is scattering is still the one producing polarization. So we are not seeing the inner ejecta, it is scattering that is creating polarization. But according to them, at this phase, we are at such a good spot that it is just single scattering. So each photon we are seeing are just
That's
singly scattered,
one scatter.
and that increases the polarization value. The reason we think that is not the case for us for this one is because we also see this change in position angle. If it was just the
Yeah.
scattering being single, then we wouldn't expect
Yeah.
position
It
angle
stayed the
to.
same. Yeah.
Yeah.
Okay.
Since it is changing, we think it might not be,
Okay.
not very sure, but it might not be the scattering reason being singly scattering. We think we might be seeing another portion of the supernova that is producing polarization of light.
Okay. 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 Good. Good.
So makes sense with the
Yeah, that was wonderful. That was really lovely. Very good. Okay. Explained
okay.
that really well. Yeah.
We
Okay.
can keep going then. So this is a lot of thing from this was actually coming from our polarimetry data, imaging polarimetry data that we used. And our result, this, like I said, follows with all the other filters. And
Mhm.
then Avinash Singh and Sergey also have papers out in 23IXF polarimetry. Our data, I think, complement each other very well.
Nice.
And when putting everything together, we are seeing very consistent behavior in all of this.
Okay.
Avinash Singh sees another portion where there is this high level of polarization. We don't have data at that phase, so we cannot really confirm or anything for that.
Okay.
So
Good for
this,
reporting. Yeah.
yeah. So this is all coming from imaging polarimetry. Now, if we go down,
Mhm. Three, and then we're gonna. Oh, here we go.
I
This is
think we can look at this plot. So
Spectra.
this is perfect. So
Oh,
this is now we can look into spectropolarimetry data as well.
okay. Cool.
So a lot is going on, but it is very, I will explain. Uh, so
Mhm.
in each panel, on top and bottom, the red and the blue, red is your polarization variation at different wavelengths,
Okay.
and the blue is your position angle.
Okay.
The black on each slide is just the flux. So how does the spectrum looks like?
Yes.
You have this horizontal kind of dashed line there. That is
Yeah.
that is the maximum interstellar polarization. So
Got it.
here in polarization for spectropolarimetry, we haven't subtracted our interstellar polarization, but you have this sense where the maximum value would have been. So you can see in earlier, so this 12.4, 13.4 are the epochs since the explosion happened.
Yes.
So you can
Okay.
see one thing very clearly, as time goes by,
Yes.
the continuum polarization starts to go towards the interstellar polarization,
Yes.
right?
Down, 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 down. I'm with you.
The first one is happening when there is this peak in the light curve.
Curve.
So
Okay.
we think there is still some
Curve. Okay.
CSM interaction happening.
Curve.
And then later on, we are getting into very, very plateau phase where photosphere is the dominant emission. So we don't really expect high level of polarization.
Let's see. That takes place within about 5 days. Yeah. Okay. I'm with you. I'm good. Yep.
Okay. So this is one part. Another very interesting thing is
Okay.
you can look at these lines and look at how does the line polarization looks like.
Okay.
So we have few lines pointed out there, H alpha, helium, and others. So for this, we have a zoomed in figure. I think it is the next figure if we go.
Gauge, looking at the evolution of that one. Let's go into figure 5. Blah, blah. Okay.
So we can look here. So what you're looking at here is the black is your flux, or how does the spectrum looks like. So it is a simple P-Cygni feature. So you have
Bang,
absorption
bang. Yep.
and then black.
Yep.
The red is your polarization. And
Okay.
you see it is inverse. And that is
Yeah.
very interesting, but also it is something we know this can happen with spectropolarimetry.
Okay.
So basically, here we are talking about one particular line that is creating this polarization and depolarization. So where you have this emission in the flux,
Yeah.
this emission is more coming from resonant scattering. So this
Okay.
is basically doesn't produce any polarization.
Yes. Okay.
Now, you are seeing this line coming towards us. In
Yep.
polarization, it is always how much polarized light you see. You divide it by the total light you are seeing.
Yes.
So in this case, we are adding this scattered light that is not polarized.
Okay.
So we are making it less polarized.
Correct. Correct. You're making your denominator bigger. Yep.
Yeah. And then on the um, on the side where there is absorption happening, so in that direction, we are actually increasing the polarization because we don't have this emission line.
Right.
So we are just seeing the scattered photons. So
Yes.
that's why we see this inverse P-Cygni, which is very interesting and telling us that this is giving us this polarization. And another interesting thing we saw that was here, the position angle really doesn't change in this line polarization. It is very similar to continuum polarization.
Yeah, we're at 14. Yes, correct. Yes, I'm with you.
So there is no change in position angle. So because of that, it tells you that this our picture that it was this photosphere expanding and this slim west interaction, because the position angle is very similar to continuum polarization, we
Yes.
think all of this are together for
Yeah.
this. So
Right.
this brings all the picture together.
Very cool.
Okay, so we use this both spectropolarimetry and polarimetric data to bring together. Now we have this very good data set for 23 IXF. So what we also did was to compare it with other normal type 2 supernova to see how does it behave when we look in a larger picture with all the other data we have.
I'm with you. Yep.
So if we go down, one thing I should say is especially for type 2 supernova, normal type 2P, we
Yep.
don't have a lot of data. So it is very limited. So we compared with few other supernova when we were comparing it with them.
Okay. I'm with you. Okay.
Okay. So we can go to the figure down there.
Let's go to 6 phase.
Perfect.
Phase. Okay.
So here, what you're looking at is the x-axis is slightly different. So the y-axis is still polarization.
Right.
So x-axis is basically we took where the plateau, like in the light curve when it falls, we basically take the middle when it is falling all the way to the nickel tail.
Okay.
And that middle is our zero value.
Okay.
So so that we can compare with all the other supernova.
Yes.
And there you see we have few different supernova and how they evolve with time
Yeah.
with respect to plateau. One thing you see is that all of them have an increase in polarization when the phase is zero almost.
Okay.
And that you see for all of them. How it behaves during the plateau phase is pretty different.
Fair enough. Okay.
Now, with 23 IXF, one very interesting and different thing is that we were able to get it very early on, that you have this first peak that you don't really see in any other supernova.
Right.
So this peak we think is coming from circumstellar interaction, which we haven't really seen for normal type 2p supernova before.
Okay.
Now, a disclaimer that with 23 IXF, you can see that we don't have data between that -50 to 0. So we cannot say for sure that it wouldn't have behaved like, say, 2012 AW or something. It could have been
Would
doing,
have. Yeah. The gap here.
but
Yeah.
we don't have that data. So that's why we just say it is
Yeah.
behaving slightly differently.
Okay. Okay. How come there's no data in this 50-day period? This was present in the other plots too.
Polarization instrument. There are not many instruments out there. It's
Got it.
very hard to get.
Got it.
We
Enough
really
said.
tried
Got it.
with
Yeah. Yeah. Yeah.
Moscow.
Got it. Got
So
it.
we compared this. Also, Nagawa et al. Have done a lot of work for this. Like they have a lot of different papers. Like if you want to learn more about like larger scale of many different supernova comparison. So
Okay.
if you go below, they have looked at how does polarization correlate with different properties of supernova.
Gotcha.
And
Yeah.
one of the things that they find very clear comparison or clear correlation is looking at explosion energy
Mm-hmm.
with respect to T-pole. So this, let's go, it's on the other side, like in the paragraph,
Okay. Yeah.
instead of
Let's get a
T-pole.
T-pole going down here.
I'm very sorry I'm making you go.
No, no, it's all good. So here we go. T-pole is the polar rise over the photospheric phase. Okay.
Yes.
So it's almost like it's a time period for when polarization
Yeah.
dominates.
Yes. So
Okay.
what they find is that there is a very clear correlation between that and the explosion energy of
Hmm.
supernova. And
Hmm.
if you see here, I know there isn't a lot of data points, but however much we have, there is a very clear correlation, and 23 IXF falls very well.
In there. Okay.
Yeah. And what this is saying us is that it is related to how much energy or how energetic the explosion was is correlated to how aspherical this explosion might have been. If you remember, the
Interesting.
reason for that is if you remember this, we are talking here about this once it falls from the plateau, how
Yeah.
much polarization increased,
Yes.
right?
Yes.
So we are saying that we are seeing the inner ejecta or the explosion, like the core
Oh,
explosion,
yeah. Yeah.
right? So if it is more aspherical, then it is saying that this, or let's say it in the other way, that is easier. If it had more explosion energy,
Okay.
then this core or the explosion would have been more aspherical. So that's why we are seeing this very clear correlation.
Got it. Okay. Okay. I'm with you.
Okay. So yeah,
That's fascinating. Okay.
so
Mhm.
what we find is that from polarimetry, I guess we can go to discussion and conclusion
Yeah.
that when we put everything together, for a lot of things, 23 IXF seem to be behaving kind of like other type 2p supernova,
Okay.
especially in the plateau and fall from the
All right.
plateau.
Yeah.
But because it was so close by and so and caught very, very early. That is another thing with transient. We are in such a amazing time because there are so many surveys, right? Like
Yes.
looking at these transients, finding them so quickly, and we are following it up like
Following up.
most of the time within 24 hours. So because of that, we were able to get there early enough to
The-
get polarization when the light curve was rising, which is very rare.
Yes.
And because of that, we saw this very early high level of polarization,
Yep.
as in our first bullet point there.
Yes.
This polarization is telling us that there is circumstellar material, there
Mm-hmm.
is interaction happening, but also this circumstellar material is aspherical.
Yeah.
And this is supported also by high resolution data as well, where they see this line structure, which are pointing towards aspherical circumstellar material.
Yeah. Good.
Now, we also got spectropolarimetry data. So here now I'm trying to put everything together.
Good.
So we got at our first spectropolarimetry data is around 12.40 days.
Mhm.
That is around where the peak in the light curve is seen. So that is where we think still a tiny bit of CSM interaction is still happening. So you had explosion. This interaction created polarization with the circumstellar material.
Mhm.
Photosphere is expanding, but it hasn't swept up all of the CSM. So you have this very, very tiny corner in that sketch we saw, and that is still giving you some intrinsic polarization.
Yes.
But the most interesting portion was there is a flip of 90-degree in position angle telling us what
Yes.
is happening and where the circumstellar material is.
Yes.
And then during this phase is also the time where we saw that reverse P signy.
Inverse pieces.
Exactly.
Yeah, yeah.
And so all of this is giving you this well-rounded one picture of what is happening here.
Nice. Nice.
And so, like, finally, this the last place is where we see this jump in polarization when the light curve falls from the plateau and goes to the nickel decay tail.
Mhm. Right. That was our gap and then a jump. Yep.
Yes.
Hmm.
And that is when it has photosphere have expanded so much, it is
Yeah.
getting optically thin. We are seeing the inner core, and this inner core now we think is aspherical, and that emission is giving us resultant polarization. And this has been seen before in other type 2p supernova as
Good.
well, because this is much easier to do because it happens much later on. And so people
Right.
can get there and get the data.
Cool. Okay.
So when we compare 23 IXF, it is very interesting supernova for many different reasons, but also we have such a good set of data. But some aspects of its polarization behavior is very similar to what we expected or what we have seen in other type 2 supernova as well. But this initial, that high level of polarization from CSM interaction is something we haven't really seen for type 2P. For type 2N we have, but this is like something the interaction happens for so long that we can get there. So this is very exciting, this high level of polarization in normal type 2 supernova.
Oh,
So from this, we were able to use our polarization data. And then this supports a lot of things that people are saying from the spectroscopic analysis and light curve analysis. And I do think like putting in polarimetry with all the great data we have from spectra and photometry gives us a very good, like a complete picture of this supernova explosion. And yeah, so I think that is kind of the summary of what
very,
we did.
very cool. Manisha, beautiful work. Beautiful.
Thank you.
Yeah, sure. Thank you so much for walking us through your very awesome article. That's great. Very cool. And you kind of touched on it a little bit at a couple of points. And so let me push on that a little bit and ask, where do you think we go from here, given the published article? You can always beg and plead tax for more time on polarimetries. Yes, but where do you think we go over the next couple of years on this object in particular, or in polarimetry on type 2Ps in general? So where do we go from here?
Oh, that's a very good question. So for this object itself, I think it is faint enough now that it will be very hard to get good polarization data.
Yeah.
We have a lot of good data though from HST, JWST, um, even like photometry and spectroscopy. So you will be seeing a lot more papers coming
Well,
up
I'm
on
sure
the
we will
subject.
on the subject.
So there is a lot of work being done. We are seeing dust formation pretty early on. So you
Ooh,
will see
cool.
papers on that, which is very interesting.
Very cool.
There is like UV spectroscopy data from HST as well, like later time, which shows CSM interactions. So these CSM are these mass loss happen pretty early on. So like it tracks how much mass loss happen at different phases before the explosion happen. So
Cool.
there's a lot of exciting work being done in this supernova and a lot will be coming up. From polarimetry side, it's not about time, I think. It is more about having instruments in telescopes. There aren't many
Okay. Okay.
polarimeter
Okay.
in
Okay.
a lot of the instruments.
Yes.
So because like we are entering such a great time for transient in general with LSST starting very, very soon.
Yep.
We will be getting so many interesting transient, but the issue is we don't have a lot of polarimeter, especially in the larger aperture telescope.
Mhm.
So with LSST, we will find much farther away transient. It will be very hard. So I'm really hoping we are trying to push for some polarimeter in larger aperture telescope. Let's hope we do that because I think that is very interesting
Yeah.
and
Provides a whole a
polarization
lot of
can
data.
play a very crucial role. Yeah.
Right. Right. Very cool. Well, it'll be really exciting to see this develop over the next couple of years. I'm excited to see the dust papers. And yeah, more petitioning for polarimetry on big scopes would be good. So very cool. Very nice. Manisha, thank you so much for walking us through your very awesome article.
Thank you very much for giving me this time. It was really fun.
Sure. And that will do, everyone. And I hope this made your supernova polarimetry day just a little bit better. And we will see you on the next one. Bye bye.